Duct tape. What does duct tape have to do with chemistry or with energy, which we're about to talk a whole lot about? Well, I want to give you an example. I have two test tubes here and I taped them together using my friend duct tape here. I now want to give this to you, and if I were to do that and tell you your job is to take apart the two test tubes, to pull them apart from each other, how would you do it? You'd probably start unraveling it. You'd work hard. Duct tape is a feisty little fella, so it takes a while to peel apart. You might try and do this, but I'd be afraid you'd break the glass. Either way, you would expend energy to get these two test tubes apart. Well, what's my point here? If I were to ask you to break a bond, would you expend energy to do that? Or would you think, oh, I am releasing energy during this process? I hope you'd realize it's the same as this principle here, where it requires energy to break a bond. And I think that's very easy to see when you think about atoms almost like they're glued together with duct tape. But when you have the inverse happen, where you've got two atoms together and you're trying to connect them, people often think, oh, I am requiring energy to make a bond form. No, you're not. Pulling atoms apart requires energy. Letting them form a bond is actually atoms' way of getting into the lowest energy conformation, meaning they're more stable now. So the energy it takes to pull them apart is significant, but the energy to put them together is not. It's actually less, it's a release of energy, not a required input of energy. And so even listen, I love these are my little snatoms, but listen, what do you hear when you put them together? You hear a noise. Noise is just waves, it's energy in a form. It's that same way. It honestly makes that noise so it can remind you that whenever you put atoms together into the form of a molecule, you are releasing energy. And when you are trying to pull them apart or breaking bonds, that is going to require energy. So requiring energy, endo, releasing, exo. Okay, so those are the big takeaways from this that I want you to see, is that whenever you break a bond, you are requiring energy to make that happen. When you're forming a bond, it's actually releasing energy because it's more stable for those atoms to be together. Therefore, it's a release of all that extra energy that they were spending to be in a less stable state. All right, so then how does this relate to a chemical reaction? Well, let's pretend you have reactants and products. How much energy is in the bonds of the reactants compared to how much energy is in the bonds of the product is going to tell you if it's an endothermic reaction requiring energy for that process to proceed, or exothermic, meaning you're going to release energy whenever the reaction proceeds. Those reactions that release energy, those would be the things that produce heat. So endothermic, you're requiring energy for them to proceed. Exo, you're releasing it. So in an endothermic state, what that means is that your energy that is in the bonds of the reactants is less than the energy that's in the bonds for the products, because you have to put energy into the system to make the product. Whereas the opposite is true for an exothermic reaction. Your reactants have so much energy that whenever they get converted into the product, there is a net loss of energy of the system. Where did that system energy go? It was released into the surroundings as heat. So when we're thinking about energy, we're thinking about how much energy is in the bonds, how much energy is in the reactants, how much energy is in the products, and we're comparing all of these ideas together.